To find the magnetic field due to current loop at axial point, we will use Biot-Savart's law, which states that magnetic field due to a elementary current length will be equal to dB. It is mu naught by 4 pi I dl sine theta by r square. Here, theta is the angle between the current element and the radius vector r. If we draw the figure, suppose this is the current loop carrying the current I. This wire is suppose upside and another is downside. So if we see at the top, the current will coming out of the plane of the sheet, and at the down point it is going inside. On the axial point P, we have to find the magnetic field. So as per the right hand rule, the magnetic field due to the current element, suppose we take this current element at the top point, and because of this current element, the elementary magnetic field at point P will be at the perpendicular to this radius vector r. This is dV, and suppose angle of the radius vector r with point P is say theta, then we can write that this angle will vertically also theta. Therefore, we can resolve this dV in two perpendicular components. One is horizontal along axis, another is perpendicular. This component along the theta is dB cos theta, and another one is dB sin theta. Similarly, if we take another element at the down point of the loop, and because of this, again there is a elementary field that is dB, and now it is in the direction at angle of theta with the downward direction. And on resolving, again we have two components. One is dB cos theta, this is also dB, and another is dB sin theta. So we can see that these two dB sin theta get cancelled, cos theta that get cancelled, and remaining is dB sin theta, which contribute for the total magnetic field due to current loop at the axial point P. Therefore, we can write that total net field due to current loop at point P is the integral of dB sin theta. And this dB is given by Biot-Savart's law. This is mu naught by 4 pi. Current in the loop is I. We are taking an elementary length dl, and angle between the radius vector and the this current element is 90 degree. Therefore, we can write this theta is 90 degree divided by r square, and sin theta is, this is perpendicular, which is the radius of the loop, and this axial distance from the loop of the point P is x, suppose. So we can write it is sin theta, which is perpendicular by hypotenuse, that is r by small r. So we can write it is integral mu naught by 4 pi I dl. This sin 90 is 1 oblique r square into r by small r, or constant terms are taken out. This mu naught by 4 pi is constant. I is constant for this integral. R and capital R are also taken constant. So we will have mu naught by 4 pi into I by r cube, this r square into r cube into r, and integral dl. This the integral dl is for closed loop, so its value will be the circumference, that is 2 pi r. So we can write it is mu naught by 4 pi into I. This r is, we can write as r square plus x square whole raised to power 3 by 2 into r, and integral is 2 pi r. Here 2 pi get cancelled with this 4 pi and remaining is 2. So we will have b equal to mu naught I into r square divided by 2 into r square plus x square whole raised to power 3 by 2. This is the total field at a point P on the axis, and it is along the axis in outward direction for the given current distribution. As a special case, if we take x equal to 0, that is point is on center of loop. In that case, magnetic field at the center of the loop will be equal to mu naught I into r square by 2 into r square plus, and this x is 0 whole raised power 3 by 2. So it will be equal to mu naught I r square by 2 into r square raised power 3 by 2. This 2 and 2 get cancelled. So it is mu naught I r square by 2r cube, or we can write P at the center of the coil is equal to mu naught I by this r square get cancelled, remaining is 2r. So this formula we have to remember. We will take some examples based on this formula.